All right, 3 more minutes. All right, time is up. Make sure your name and ID are on that quiz. Pass those quizzes to your left. While you're doing that, and before some of y'all leave, I want to draw your attention to the very top right board. The top right board. So if 80% or more of y'all fill out the course eval, then everybody gets 5 points on their final. So do course evals. Do those. Those are important. They're important for me because most places will use course evals from students to evaluate me and my teaching. It's unfortunately very important. The unfortunate bit is not that I don't appreciate y'all's feedback. The unfortunate bit is just that there's more to teaching than what y'all see. And so it would be good if I were evaluated on more than that. However, please fill those out for me. So the benefit to you, 5 points. Benefit to me, I get rehired. Benefit to future courses, right? Benefit to future students. The comments that you give me, I actually read. It takes me usually a couple days once they get released to me, but I go through them and I try and figure out what were the things that people thought worked well? What were the things that people thought didn't work well? What were the things that weren't even on my radar that they wished I had done? Right, so when you're filling out those course evals, the numbers are fine, right? That 1 to 7 Likert scale is what it is. But it doesn't give me much info. Okay. So I know that I'm probably talking about something you don't care about, but please, thanks. It's actually important to me because I want to be able to teach people better in the future. So if you tell me what you thought went well or what didn't go well, I can improve in the future. So that'd be great. Thank you for that. And I talked to Audrey. If her evals hit that same mark, like greater than 80%, she requested that people get 5 points added to their quiz scores, which seems like that would be pretty, like a non-small thing. Yeah? Okay. So there we go. If you do course evals, you get 10 points added to your score. Yeah. I assume it's all up in there? Like it should all be in there together? It should be. If it's not, I don't know who to go to fix it. It is? Totally there? Okay. Cool. Remember, so today we're talking about our atomic orbitals and molecular orbitals. And before we can talk about those, we need to remember exactly what are these atomic orbitals. What we've talked about over the past couple days is where the data came from, right? We drew atomic energy diagrams back in Unit 1. And then we learned that a lot of that data came from spectroscopy, right? Shined light or very fast-moving electrons at a sample and then measured what came off, right? So that's what we have done, and that's the data that we collected. And the answers to that data are here. Right, so we got energy going up. We have our 1s orbital. We have our 2s and our 2p orbitals. And we have our 3s, our 3p, and our 3d orbitals. Yeah, these are the answers. Right, so the numbers 1, 2, and 3, and that corresponds to something pretty important. Right, so our number, that's the n value, is our principal quantum number. And that correlates to the energy level. Right, that's the energy level of that particular compound, right? So energy level being horizontal bits of the periodic table. And then we have these letters. We have our S's, our P's, and then D. Right, so the letters are giving you a more nuanced flavor of what that energy level is all about. Right, so our letters are the subshells that give info about the shape of these orbitals. All right. Let's see. The horizontal line, right? Like I kept drawing these horizontal lines. Like what does that horizontal line really mean? This horizontal line represents the energy of an electron in that orbital. Solid. Right, so the energy of a 1s electron is down here. And then 0 is way at the top. Right, all of these energies are less than 0. All right, the other thing, and I can't remember if I've used this word or not, but if you have multiple orbitals of the same energy, right, so degenerate orbitals have the same energy, but different spatial orientations. Let's try that again. Orientations. Nailed it. Yeah, so the p orbitals all have the same shape, right? Peanut, but they're x, y, and z. Right, so same shape, just pointing in different directions. That's what we're talking about with spatial orientations. Right, and so the 2p orbitals, all three of them, we call them degenerate. And that's just the fun word for it. The other thing I want to draw y'all's attention to is that right here, this bit, 1s's, 2s's, and 2p's, yeah.
Why are those degenerate?
They have the same energy level. They have the same energy. It is defined as same energy. Yeah. Yeah. So if they're all in that same line, they're degenerate to each other. So 1s, 2s, 2p, this is our money spot. This is what we've been really focusing on all semester. This is our Chem 1A focus. And the reason we're focusing on it is if you look sort of at like what has 1 and 2 energy levels, you got your carbons, your hydrogens, your oxygens, your nitrogens, your fluorines, pretty much the stuff that makes you. Right? Like most biological compounds are focusing on the 1s's and the 2s's and the 2p's. There are some atoms in us, right? Phosphorus is the big one. Sulfur is another one, where we have to look at the third energy level to figure out exactly what's going on with those atoms. The fun part is the shapes are all the same. Right? So like the 3s looks like a 2s, looks like a 1s upon like, a If you squint your eyes, they look about the same. Like, that's fine. So we're not going to really go into it too much. Do I have any geologists in the room? Geology. Anybody else? Word. Yeah, I'm sorry. There's a whole block in the middle of that periodic table that we just didn't touch. And that's where most geology things happen. Same thing with the left side of the periodic table. My bad. And so that, important, but I only had one semester to teach a full year course. And so I had to say, what is 1A a prereq for? And it wasn't a prereq for anything geological. Unless it is it? It must be if you're here. Sweet. I appreciate you. Cool. Most of the things there have to do with how do all these different, like if I have a crystal, where do all the atoms fit? And so there's things like crystal packing. You've got field theory. Some of the cooler parts of geology actually build off of what we're going to talk about right now. So as long as you have the basics, you'll be able to figure out the rest. Cool. All right. So what we're going to talk about is how do we then take these atomic orbitals that we've learned about in Unit 1 and turn them into molecular orbitals. We have already talked about sigma bonds, right, handshake, versus pi bonds, shoulder bump, or high five, depending on how you're feeling. Right, so we've talked about the like how those orbitals come together to make bonding type orbitals. We're going to dig into that a little bit deeper today. Right, and so what we're going to see is that to make molecular orbitals, or to make molecules, atomic orbitals, AOs, combine to form molecular orbitals. MOs. Right, so that's what we're going to deal with. And what we have to conceptualize is that these orbitals are acting as waves. All right. Have y'all heard of this Schrodinger person? Schrodinger. Dude was a legend. He wrote this equation. He was like, I know what I'm going to do. I'm going to do it. I'm going to write the equation for the hydrogen atom. Everyone looked at him like, really? You're going to write the equation for the hydrogen atom? And he was like, yeah, me and my cat. We're going to sit here and we're going to write this. And then he did. Dude actually did it. And so like there is an equation. It's called the wave equation. Bam! That perfectly describes the hydrogen atom. The electrons that hang around a hydrogen atom. It's real baller. Like that is super impressive and crazy considering that he did this well before computers were things, right? Like he just did that with his head. Like his brain was different than normal brains. It was amazing. So because of that, right, every other orbital that we're talking about, all the other atoms, we take the hydrogen atom wave equation, then we perturb it a little bit to make it fit whatever our new atom is going to be. Right? But still, we take a wave, we sort of change what that wave is going to do to get different atoms. So we're conceptualizing all of our orbitals as waves. And so if we're going to do that, we have to think about how do waves interact with each other. So we've got a wave and another wave, and they are traveling towards each other. Traveling toward each other. What happens when they bump into each other? What is that wave going to look like? It's going to get hella big, right? We're going to do some of that. Right, I gave it a camel hump, a double camel hump look, because maybe they didn't get all the way towards each other yet, right? And what I want you to try and visualize for yourself is that you can do this. So this is the combined waves in white, or you can just say that's what the two individual waves looked like, and we just put them on top of each other. Both of them are fine. I just want you to know where this all came from. And so what we're seeing here is that the waves combined, and we say that they combined constructively. Yeah, they added together. The word for this, or the phrase for this that we're going to use due to waves, is going to be constructive interference. All right, so we saw constructive interference, the wave got bigger. Now what we're going to do is apply this concept to actual atoms. All right, so first we're just going to remember what are the shapes of our atomic orbitals. And we're going to look at the s orbitals. It's a sphere. And then the p orbital, which is a peanut. All right, so if this is our nucleus, we get a sphere. If this is our nucleus, we get a peanut. All right, so those are the overall shapes. The problem here is that we're looking at a 2D cross-section of that 3D shape. All right, so what we can draw on paper isn't necessarily what it really looks like. So this is our 2D representation of the 3D orbitals. Right, and trying to think about like why is it 3D? How do we go from a wave to this 3D thing? Right, because when we draw the waves, we're always drawing it sort of in two dimensions. Right, it's going left to right and up and down. The wave equation is telling you, yeah, it's actually in all three directions. And so when we see that, when we draw that, we have to come up with this way of showing our picture. Right, so these pictures are coming from a very specific mathematical. We did math. All right, so to get our 3D pictures, we square the wave equation. And this gives us a probability function. Am I going to make you do that? No. But I want you to know where that picture is coming from. Right? It's not just from nothing. Like Schrodinger didn't just think, I feel in my heart of hearts that this s orbital thing is going to be ball-shaped. That's what I feel, and so I'm going to make my math agree with that. Like, no, he did his math, and then he got a wave, and then we, as non-Schrodingers, were like, what does it even mean? And so we had to make it look like something. Right? And so we made it look like something. We brought it into 3D space in a way that made sense. We get these pictures. So we get a sphere and a peanut. Now the reason I'm talking about squaring it is it's right here. Let's talk about it. So if we have our atomic orbitals coming together to make molecular orbitals. Right, that's the concept that we're rolling with. And if we're doing this for H2, then my atomic orbital is H1s plus H1s to give me something H2 related. Right, again, this is our just conceptual goal. And so what does the H1s orbital look like? It's a sphere. But what does its wave look like? Right? If we step back and say, well, what was that wave? Yeah? Yeah? These come together, boom, boom. So they come together. All right, constructive interference. All right, so this is all leading to some very delightful constructive interference. But the way that I want you to see this is I've drawn this in one particular way, right, where I kept the outlines of both original atomic orbitals. Totally fine, totally fair game. Or, if you want, you can show what they look like when they add together. Both are thoroughly okay. Both of those are ways that you can talk about this particular wave. All right, so we've added the waves. To get to this, right, we did two things. So, right, we're there, and then we square it. Square the wave. When you square this wave, what's going to happen to it? It'll just get hella big. It gets yet bigger. Okay. So I'm squaring this wave. Yeah? Squared it got bigger. And then here, to get to this, 3D if I. All right, so if you take that 2D wave that you're looking at, that probability function, imagine that this reference line, is a stick. Spin the stick. Spin the stick. What shape do you get? That. It's more football looking if you go with the heights that I gave you. But it pretty much just looks like what we drew. Right? So you have your reference line on a stick, you spin it, and that's your 3D shape. It's not perfect, but it works well enough for government work. Us being at the #1 public university. This is in fact government work, so it's good enough for us. Let's go. Okay. So, some cool things here. This, right there, and right there, is increased electron density between the atoms. And so we have increased the electron density between those two atoms, right, which is leads to a bonding orbital. Right, and so this right here, constructive overlap. Right, we had our atomic orbitals that constructively overlapped. We got that picture, whichever way you want to think about it, giving us a bonding orbital. Now what I want to ask you is a very hell of important question, and I ran out of room for it, so I'll just put it up here. The energy of 1s is greater than, equal to, or less than the energy of the bonding H2MO. Let's fix that. Let's do a little bit of editing. All right, so the energy of the 1s orbital is either greater than, equal to, or less than the energy of the bonding H2MO because. All right, so take a minute right now. I feel like you're going to have a pretty good handle on which of those orbitals should be higher in energy. The because is what I need you to talk about. All right, so give it 30 seconds. You get 30 seconds to figure this out. All right, that was a quick 30 seconds. It was a quick 30 seconds, but an actual 30 seconds. So, you're going to lean to the side that's bigger. If E1s is bigger, lean to your left. If the energy of the bonding orbital is higher, lean to your right. So lean to the side that has the higher energy. Lean to the side that has the higher energy. Which of those orbitals has a higher energy? Okay, so that's 50-50, which means most of y'all are wrong. Try again. Talk about it again. Because people who were sitting next to each other chose different directions. That's some bullshit right there. So try again. They're bad at it. Y'all bad at this. Let's do better. Let's go. No idea. All right, lean again. Lean again. Lean to the side of higher energy. You're leaning to your left if 1s is higher. You're leaning to your right if bonding is higher. Which is higher? Which is higher in energy? All right. What does bonding mean? Is perhaps the minimum of potential energy? The minimum. The lowest. It be low. Yeah? Remember your bonding graph? It did one of these. Yeah, it did one of these. Was down here. That's your bonding. Bonding should be the lowest in energy. Okay. Why? Why is that bonding lower in energy than the atomic orbital? Yeah. Okay. More stabilized because it's hella happy. All right. Because it happened? All right. It's a bond, yeah? Bonding? What is true in bonding? What's happening to the electrons if it's bonding? Yeah, they're in between the two nuclei. So Coulomb's law, what's that going to tell you? You have more negative charges and you have more positive charges and the distance is smaller. Everything involved there is giving you a more attractive force or a lower potential energy. Yeah? And you may be wondering, but what about all the repulsive forces, right? That also is going to be true. But at the bond length, you've minimized your repulsive forces and you've maximized your attractive forces. Right? So the energy 1s is bigger than the energy bonding because bonding MO has minimized repulsive forces and maximized attractive forces. All right, for homework, get this. Get it. Get this. Understand that. Yeah.
That's a good question on jams. Could you also just say it's more stable? The bond is more stable?
So we cannot say that because it's more stable. And so that is the truth. Right? So the truth there is yes, the bonding MO is more stable. But the why, why is it more stable, is the thing that we're not getting to there. And so you got to go into the physical pieces of it. What are the charges doing that are making it more stable? Okay. So what we did, right, if we're looking at that, we're looking at that question and be like, okay, so I had these high energy things and I ended up with a low energy thing. What did we just do to the universe? We just destroyed some energy. It just disappeared. Right? We started high, we ended low, and that's it. That's not allowed. Right? So to make sure that we don't break the rules of the universe, we have to give it something back. Right? So if we constructively interfere, we also have to do something else to make sure that we make a spot for those electrons that's higher in energy. We have to equal out what we're doing. So what we're going to talk about is something called the conservation of orbitals. When really I'm just talking about the conservation of energy. Right? If you start with two orbitals, you have to end with two orbitals, no matter what they might be. Right? So number of starting atomic orbitals must equal the number of ending or new molecular orbitals. Right? Whatever you start with, you have to end up with that same number. And to do that without breaking the rules of the universe, we also can't have them both be lower in energy. Right, so we started with two 1s's. We have to end up with something that's higher in energy. To do that, we're going to check out another way that waves can hang out. Right, so now we have two waves. I tried to keep that reference line in the same spot. One of them is now a plus wave. That's not a charge. That's just a mathematical sign. Right? It has density above the reference line. So these, not charges. Just mathematical signs. Mathematical signs. And then we call them phases of the orbital. All right, so that plus, we say, hey, K. It's a positive phase versus a negative phase. When those come together, right, you have something above, something below. Those come together. They cancel each other out. So what it's going to look like is that. And so this is called destructive interference. Destructive interference. And that's fine. And here is where me going into like, hey, how did we actually get to these waves? How did we get from wave to orbital is going to come in handy. Right? Because if you square this, right, if you square this to get the orbital shape, they're going to look like that. If you bring those two together, you would think they combine constructively. However, that squaring is something that we do as people to visualize that thing that's going on. Right? That's something that we're doing, not something that the equation is doing. So when we square it, we have to remember what phase did it start as. Right? That negative mathematical sign goes away, but that negative mathematical meaning doesn't. All right, so what I'm going to do is fill it in. Right, so now this shading is indicating phase. Right, so we have unshaded and shaded. Those are opposite phases from each other. All right, so then when we bring these together, they cancel each other out as they get closer. And if you spin it, if you 3Dify it, you get this. That is your anti-bonding molecular orbital. That whole thing, both pieces of it. It's not two orbitals, that is one orbital together that we're calling the anti-bonding MO. And what we have here is something called a node. So there's no electron density. And so that just lets me talk about how cool electrons are again, is they can teleport from the left side of that line to the right side of that line without ever going through that line. They never go through it. They just zip from spot to spot using quantum space or something. I don't know. Quantum things. That's badass. It's so cool. It's so cool. It is the business. All right, so this anti-bonding MO is showing you like, hey, yeah, electrons don't care about space. Space. Yeah, they go wherever they want. And that is incredible. That is just incredible. Okay, so if we then liken this to our hydrogen picture, right? Like these were waves, and then we remember, okay, so that's pretty much like saying H plus H, giving us an anti-bonding MO. So what we're going to take is the 1s, and we're going to add it to the negative 1s. Right? I added two things, I subtracted those two things. Overall, I did nothing. Right? So mathematically, we're okay with the universe. Bring these together, you get that picture. Right? So this was our destructive interference. And now we've made an orbital that's higher in energy than the other ones. Why is this one higher in energy than the bonding? How far away are the nuclei? Are they the same distance, farther away, closer than they were in the bonding? Exact same place. It's okay. This is nonsense, right? Like, what on earth is antibonding? What does it even mean? Right? And so, one sec. So what we're doing here is we're saying, I'm bringing these two nuclei here. I'm then going to constructively overlap the orbitals and destructively overlap the orbitals. You do both to make sure that the universe is okay. Yeah? So you constructively do it, we get very low energy. If we destructively overlap, why does the energy go up? Physically. Like Coulomb's law me right now. And so here are my nuclei. They're here. The bonding situation, I go down. What about the bonding situation allows this energy to go down? Right, we've minimized repulsions and maximized attraction. So I had a whole bunch of electrons between these two. Right? Positive charge, two negative charges. My charge portion of Coulomb's law is at 4. Yeah, that's big. Now I'm here. And I've decreased the electron density between the two nuclei. What should happen to the energy? I've decreased the electron density between the two nuclei. What should happen to the energy? You have an option, and you already know the answer. It should increase. Why is it going up? Because now you've got positives repelling positives. I have two positive charges right here with not much negative in between them. That should increase the energy of that orbital. Yeah? You with me? You better be. That is the other thing. Get this. What's up? It would take less energy to break up the orbital, which is true. If I put an electron in there, it is easy to separate those two atoms from each other. So those electrons are higher in energy. Right? All of these energies are below zero. Right? Like all the energies are below zero. And what we're doing is saying, like, how far below zero is it? And so the bonding one, hella far below. Anti-bonding, not that far below. And so if I want to get rid of that electron, it doesn't take much work. Okay, I have exactly 5 minutes to do 10 minutes of things. You have a weekend to grapple with knowledge, please. Please have the grapple. So what we're going to do? What we're going to do is construct an MO diagram. All right, so MO diagram construction has the same 6 steps no matter what you're doing. So the first step is you draw the Lewis structure. Second step is you count the valence electrons. I mean, to be fair, you probably do this in opposite order. Like, I assume you count, then you draw. Either way, both of them have to happen. Third, figure out, do you have to hybridize any atoms? Fourth, you construct the MO. All right, this is going to be 3 steps on the next board. Fifth, you take those valence electrons and you add them to your new MOs. And so put electrons into new MOs. And then sixth, analyze the frontier molecular orbitals. That's something that we're going to talk about later on next week, probably Wednesday. All right, but these are the 6 steps that we do every single time. Never fails, never deviates, it's just these 6 steps. All right, and what we're going to practice with is constructing the H2MO diagram. We've already got the pieces. We've already done the intellectual legwork on these previous 2 boards. What we're going to do now is say, how does that look on something that we call an energy diagram? Right? How do we vertically separate them in terms of energy? Ooh. Okay. So, step 1, HH. Step 2, 2 electrons. Step 3, no hybridizing. Because hydrogens. Right? Hydrogens have the 1s orbital. You don't hybridize that with anything because it's just the 1s orbital. The shape that you have is 1s. Yeah? So we drew the Lewis, we counted the electrons, we're not hybridizing anything. So number 4 is we're going to construct. So I'm going to start you off. We have an H, we have an H2, and we have an H. So what I'm doing here is organizing my atomic orbitals. Organize atomic orbitals to create new MOs in the center of the diagram. Right, so we have everything that's going to be, like all of our atoms are on the outside, the molecule is on the inside. So atom, molecule, solid, atom. All right, for B, the next step is place atomic orbitals on the energy scale appropriately. All right, so here's our diagram. Our energy scale is the vertical scale. And you're like, okay, what do I do? You pick a spot. You pick a spot and say, great. It's my H1s. You then say, what should the other hydrogen be if I put the first one here? Should its energy be any different? No. Right? You pick a spot and you're like, cool. My other hydrogen, since it is also a hydrogen, should have the exact same energy. Right, so we set it up. Then we get our energies figured out. And then C, mix atomic orbitals constructively and destructively to get new MOs. All right, so we had our 1s orbitals. And we're going to mix them constructively, which is 1s plus 1s, to give us the new bonding type molecular orbital. Constructive interference for new bonding H2MO. The term that we're going to use here, right, we know, again, from Unit 1, the way that those orbitals overlapped. We increased electron density along the internuclear axis. What type of bond is that? Right, handshake versus high five? Sigma. This is a sigma HH. All right, then we're going to do destructive interference. 1s plus the negative 1s is going to give us our antibonding. So destructive interference gives antibonding MO. So that overlap, the way that those two atomic orbitals came together, is it different than it was before? No, it's still along the internuclear axis, so it's still a sigma-type molecular orbital. But it's no longer bonding, so we have to say it's different than it was before. The notation we use for that is a star. Right, so that destructive interference we denote with an asterisk next to the flavor of that overlap. Okay. Steps 5 and 6 we can start with on Monday. All right, y'all. Much love. Have a good weekend. And I will see you on Monday.